Hey, all you sexy C++ programmers. You smart. You loyal. You a genius. I'm Chili, and today we are going to make a freaking bloom filter for the HUGS engine. And it's going to be so sweet, you are going to bust a load in your pants. But pictures speak louder than words, so let's pull up the new branch and break a little piece off. Break a bit off of that Kit Kat bar. Where is it? Branches. Here it is. We want a new branch, and we want to go to soft bloom. That's what we want. Create that branch, and let's take a look. I guess we'll just build it. That's the fastest way to go about this whole shebang. All right. So here's what bloom looks like. I think you'll agree it's pretty fucking sweet. Let me get my controller here. Yes, I have seen the future, and it is bright as fuck. See, now maybe you get an idea of why I chose the lightsaber sound effect for this. This does have kind of a lightsaber-esque look to it. But anyways, that's what we're going to be doing today. Now the question is, how do you achieve that effect? I'm going to show you. Let's just take a look in Photoshop, shall we? I'm going to go to Bloom. Yeah, that's what it is. So here I've got a bunch of figures here, and we are going to bloom process it. It's a very simple process, and yet complicated at the same time. It takes a little bit of math, but we'll get through it. Trust me. I've only done this once before. Safety is not guaranteed. But anyways, what I'm going to do is I'm going to copy this layer here. We'll just drag this down here, and we'll turn this layer off. Now what we want to do with this layer, the first thing we want to do is we want, oh yeah, so you can see this. We want to filter it. So we're gonna apply a Gaussian blur to this mother. And yeah, we'll put a radius of 15 pixels. Okay. So the first step of bloom is blur. You blur whatever stuff you want to create the bloom effect for. And then all you got to do is apply that back to the original image. You add that on top. So you don't blend, you actually add on top. And that has the tendency of making the original underlying pixels brighter. Tends to drive them closer to white, actually. And it also, you get the halo effect from the bloom stuff. Here's without the bloom. Here's with the bloom. I hope that shows up okay on YouTube. But it does make it look a little brighter. But that's the general idea. You bloom, so you copy, you blur, and then you add back onto the original. Alright, so that being said, how are we going to get this done in code? How are we going to compute this? Well, the main difficulty is going to be the blurring. How do we process blurring? Blurring is a kind of filter. And filters are done with something called a convolution. Convolution. What is it and why do we give a fuck? So, we're going to look at it to start with in a one-dimensional system because that's a lot easier to work with. So let's say you've got a one-dimensional signal here. It could be a sound signal, it could be something else, but let's say it's a sound signal. Convolution filters are often applied to sound as well. So you've got this signal here, and it's a discrete signal. So you've got these discrete data points. Just like in a image, pixels would be discrete data points over space, as opposed to continuous changes. Now you've got something called a kernel. And a kernel is the thing that's basically your filter. You are going to do a convolution between this kernel and the original signal. In this case, they happen to be the exact same thing, but in general, they're going to be different. And when you perform the convolution, when you're done, you're going to get some result. So how the convolution works is very simple. You take every point in the kernel and you multiply it by the data points in the input signal. So if we take this the way it is right now, we multiply this point here by the point in the data signal, which is 0. You get 0, 0, 0, 0, 0, 0, and then here 0, 0, 0. So the output is going to be, so here's the first one. Now what you do, you slide that motherfucker over by one data point value, one pixel, whatever the fuck you want to call it, one sample, and you multiply them again. Again, it's 0. Then slide that motherfucker over again. And now we've got a value. We've got 1 times 1 here. These are all 0, but this point here, the product is going to be 1. So now we put a 1 here. And again, slide, multiply, 0, 0, 0, 0, 1, 1, 0, 0, 0. So you add all the products together. So before, it was 1. Now it's 1 and 1, that's 2. Put 1 here. We'll just fudge it. And then you slide over by 1 more pixel. And you're going to be like here. I don't know why the center is getting off, but it's probably because the way I drew the signals isn't quite up to snuff. The distances between the points aren't very consistent, are they? No, they are not. Oh, and then I fucking drew on the... Okay, well, you get the idea. The idea is you slide this motherfucker along here, and as you're sliding, you're multiplying and adding those... Fuck you. Okay, you're adding that shit together. Now, as you get to this point, slide to here, and now you're going to be decreasing. So you're going to go down like this, and then that, and there you go. So there is your convolution, your one-dimensional convolution between your kernel here and your input signal. You get this triangle wave like this. That's how it's done. So let's take a look at a little sweet app that is going to demonstrate this better than my dumb diagram will. We'll take a look at simulation of convolution. So here we've got, this is output signal, but it's not really. This is the input signal. This is the output signal, and this is the whatchamacallit, the kernel. So we're going to use this square wave rectangular signal kernel, and we're going to apply it to this pulse train here, and we're going to see what we get. So you do a convolution between the rectangular and the pulse train, and what you get is you get a bit of like you get an integration type deal, and it's almost like a bit of a smoothing function here. It smooths out all the bumps between here, but it still looks kind of jagged. What if we were to replace that with this kind of bell curve here? This is called a Gaussian function, or a normal function. But this is the function that's used in the Gaussian blur. And if we apply that, we see we get a much smoother blurring effect here. Overall, it's a very similar shape, but this one's much smoother. So that's why we want to apply the Gaussian as opposed to, say, just a simple box filter. Gaussian looks much better. Now, how does this work in 2 dimensions? It's quite similar. What we do is we have an input image and we have an output image, and then we have a kernel, which is a 2D kernel. So it's like a matrix. And you take a point on the kernel here. So if you position the kernel like this, you're going to be creating this pixel. You're going to be filtering the image to get the output pixel for here. And what you do is you multiply every element in the kernel by the corresponding overlapping element in the input image, and that will get you this pixel here. And then you slide that kernel, everything's a slide, I know I fucked it up, but you slide that kernel along the input image like this and generate all the points in the output image. And that's how you do it. That's how a 2D filter is applied to an image. Now, if we use the Gaussian, what does a Gaussian look like? It looks like this. Here's a Gaussian 2D. Here's a Gaussian 3D. This is what your kernel will look like. Now, in general, the Gaussian function is infinite. It doesn't stop after a certain point. So what you're going to get is to apply a perfect Gaussian to your image. Let me just get this out of here. And let me just undo a whole bunch of dumb bullshit. So to apply a perfect Gaussian image to your, or the Gaussian kernel to your image, you're going to need a Gaussian kernel that's like this big, or maybe a little smaller. But so your kernel is huge, ladies, and then you slide that kernel along here and generate the output, because the kernel doesn't stop. It goes on to infinity. Now, if you do this, what you're going to end up doing is for every pixel that you process, you're going to be multiplying. You're going to be doing n times, or you're going to be doing n times n times m multiplications for every pixel, and you have n times m pixels. So that's n times m squared. Now, if you make the simplification, shit, I can't speak today. I am fucked. That n equals m. What you're going to get is n squared times n squared, n to the fourth. That's your complexity. That's your big O, n to the 4. That is fucking insane. That is a lot of processing. So you don't want to be running your filter that has time complexity of n to the 4th power. So what do you want to do? Well, the Gaussian, you can specify how quick it rolls off and everything. The shape of the Gaussian. So what you want to do is you want to limit the size of your kernel. So the size of your kernel is going to determine how far your blur can extend. And you limit the size of your kernel to say like 7 pixel diameter, or like 16 pixel diameter or whatever. And then you tailor your Gaussian so that it rolls off and it hits very close to 0 at the end of your kernel size, your kernel extent. You don't want, like, for example, you don't want your kernel being like ending here, because your Gaussian is going to roll off and then jump to 0. You want to end your kernel like around here. And if you want your kernel here, then you want to make your Gaussian more like this then. You get it? So you tailor that looks like a big dick, I'm just going to say. But anyways, you tailor the shape of your normal function, your Gaussian, so that it rolls off nicely to the extent of your kernel. And if you do that right, then you can choose a kernel size that's, much smaller than the image. And in that case, your time complexity is going to be a lot easier. Let's say that your image has has n squared pixels. And your kernel is, the dimensions are k by k. So that's k squared elements in your kernel. And your complexity is n squared times k squared. It's a little bit off. I mean, obviously, when you are computing at the very edges of your image, these computations don't need to be made. But in general, the asymptotic value is going to be n squared times k squared, which is better than n to the fourth because k is going to be much smaller than n. But we can do better. And the reason we can do better is that it just so happens that the Gaussian blur filter is what is known as a separable filter. So instead of sliding around this two-dimensional kernel over the entire image and computing all the multiplication of all the coefficients, adding them all together for every single pixel, what you can do is you can split up the operation into a horizontal pass and a vertical pass. And so what you do is in the horizontal pass, you treat every individual line of the image as its own one-dimensional signal. And then you just apply your standard one-dimensional convolution to that signal. So you do a one-dimensional convolution for every line of your image, and that will give you an image that is blurred horizontally. So it is blurred in the horizontal direction. And then you do the same thing in the vertical direction. And that will give you your image that was blurred, will give the same result as an image blurred with a 2D convolution kernel. So separable filters will allow you to do that. And this will be quite a bit faster. So with the 2D version, you've got n squared times k squared. With this version, what you're doing is you're doing a 1D filter for every line. So you're going to do, the 1D filter has k multiplications, and you're going to do that for every pixel. So you're going to do n squared k. And because you have to do a vertical and horizontal, the result is 2n squared k, which is much faster than n squared k squared. As long as k is, bigger than like 2, you're going to get a good speed up by splitting up your filter into horizontal and vertical. We are not done yet. We can make this even better. Now, the way we can do that, first of all, take a look at this expression. This is our time complexity. You'll notice that our most problematic term is this n here. That's the size of the input buffer. If we can do something about this, we can make our life easier. Now, what you notice, what we're doing here is we're taking an image and we are making it blurrier. Now, what would happen if instead of taking the full image and making it blurry, what we did was we reduced the image by half in both directions. So we reduce it down to this size here, from this size to this size, and then we process the smaller image, and then we blow it up again. Now, in general, if you take an image and you downsize it, and then you size it back up again, it gets blurry. But that's what we're doing anyways. We're just making an image blurry. So by downsizing the image first and processing the downsized image and then resizing and adding to the original, we lose very little quality, but we gain a shit ton of speed. Now, obviously, there's going to be a limit to that. I mean, you can't downsize the image to a single pixel and then process that single pixel and then resize it, because you'll just get a gray haze over the entire image. That's not going to work. But we can get a pretty good downsize. In in the system, I'm going to downsize by, I'm going to divide the width and the height by 4. So it's going to be a 16 pixel down to 1 pixel downsize. Then we process the downsized image, and then we blow it back up to the original size with bilinear filtering, I guess is what it's called, or interpolation. That's the word I'm looking for. Interpolation. So, all right, another issue to consider is the fringe, not the TV show with the guy from Dawson Creek and the old man on drugs, but rather the edges of our filtered image. If you take a look at this here, the situation here, we're calculating the top left pixel for the output. And as you can see, inside the convolution window, we've only got about 1/4 of the input image. The rest is just garbage, I don't know, or 0. And so what's going to happen is you're not going to get a full input in the input window to put in the output. So the situation that this creates for us is not a good one. In this case, let me just move this around here. So in this case, everything inside of this region here is going to be okay, but everything outside of it is going to be messed up. So what you get is you get the proper results for a window like this. And this part here is going to, the blur is going to fade out to black. It's not going to be as strong as it otherwise should be. And that's a problem. It's not going to look good. So what my solution to this, it's very simple. Thank you very much. It's, let me just change my, my goddamn layer here so my shit doesn't move on me. So in the input, we are going to overscan our rendering. So we're going to render in a window, maybe something like this. We're going to render a little bit of extra resolution there. And then when we process the filter to the output, we are going to have that fringe region there to supply our kernel, our filter kernel, with data so that I can output a proper image. So we're doing a little bit of extra work, but it's fairly small compared to the size of the overall size of the resolution. The size of the fringe, it's easy to calculate. You take your kernel size. So let's say our kernel here has a radius of 8 pixels. That's the actual thing we're going to use. The whole size of the kernel is 16 pixels. So the radius is 8 pixels. So that means that when we're doing the filtering, we need an 8 pixel fringe. Now remember, before we filter, we're downsizing. So what we actually need, because the fringe is also going to be downsized, we need a fringe that is you have to multiply the fringe that you need by the downsizing factor. So if we're downsizing by 4 in each direction, we are going to need a starting fringe of 4 times 8, 32 pixels, in order to generate our 8 pixel fringe in the downsized image, which will then be blurred. And then when we upsize it again, then we get our 32 pixel fringe, which is just going to contain garbage, and we don't actually use that. We just use the non-fringe image then to copy to the back buffer and display to the screen. Now, this brings about one more interesting point, and that is that when we do our blur step, our Gaussian blur, on our downsized image, we're going to have a blur of a radius of 8 pixels. But because we're working on a downsized image, when we upsize, we actually get a blur radius of 32 pixels. So we get a bigger blur radius, and we have to work on less pixels. So downsizing and then resizing is a very, very nice solution to this problem, especially since that the loss in quality is not going to be very apparent in a blur situation, because you're blurring anyways. So that is the last thing I wanted to talk about before we get into the code. Now, this fringe system is going to necessitate a few changes in our the base of our drawing code now. We're going to need a larger back buffer to hold the fringe region. So what I've got here is here where I create the sys buffer. Before it was just view width and view height. And now I've changed that to view width plus bloom processor get fringe size times 2, right? Because you need the fringe size and you multiply that by 2 because you've got, you know, right top or the right and left side. And here you've got the top and the bottom side. So you multiply fringe times 2, add that to your view dimensions to get the size of your sys buffer, including the overscan fringe region. And then when you draw it, when you present that bullshit to the screen, you are going to need to not present the entire sys buffer, but you only want to present the region, the center region that does not include the fringe. So you've got this loop here that is going to do that for you, just presenting the central region of the system buffer. So one more little caveat of the changing of the system buffer is that now everything that you draw has to be displaced by the fringe. So what you do is you set your viewport so that the viewport's dimensions are the view region that does not include the fringe. And then you have to make sure that in all the things that you're drawing, you take into account the offset that the viewport introduces. So here before I was just drawing this with like absolute dimensions right onto the screen because it wasn't part of like the whole the camera transformation or anything. So I was just doing the lazy thing and drawing directly on the screen. But now I'm actually taking into account the translation introduced by the viewport and using that there. And the lap display, same thing. I get the offset by looking at the translation vector or the transformation vector, and I extract the translation component from that and and then add it. Don't worry about, you know, rotations or anything because we're not going to be able to rotate our GUI. It doesn't make any sense. But we do have to now look at the translation because of the whole fringe situation. All right, so let's take a look at the actual bloom processor. Here it is. Here is the initialization. We won't look at that right now. We'll take a look at that a little bit later. The first step in drawing our bullshit, well, here you have the go function. It's got some stuff here for diagnostics, but the main stuff is these functions here: downsize, pass, horizontal, vertical, and upsize blend. So let's look at those in order. First off, the downsize path. This is very simple. All you're doing is you're taking those 16 pixels and you're adding them together and dividing by 16. You're just averaging 16 pixels together to downsize to 16 to 1. But there is also one other thing that this function does, and that is a little interesting. So you see here, what we're doing is we're not just adding them together, we're also multiplying them by x, and x is equal to basically the alpha component of these pixels on the back buffer. But as you know, on the back buffer, the alpha component doesn't mean anything. Alpha is what is the channel in the sprite that you use to blend the sprite onto the back buffer. But once the data is on the back buffer, the alpha channel doesn't mean anything. It's just garbage. So we are going to reuse that empty space, and that space is going to signal how much of the image is actually input into the bloom filter. So we're going to scale every pixel by this X value, and that will allow us to selectively add bloom to different components in the image, and to give more to some and less to others. So we're scaling by X, and then we're averaging all those together, all the channels together, RGB, and packing that and putting that into the output buffer, which is set to H buffer. The The Bloom processor has two buffers that it uses to store the intermediate results of the horizontal and the vertical passes. So the flow goes, you go from your input buffer to your H buffer. Then you go from your H buffer to your V buffer. You go V buffer back into H buffer, and then you take the H buffer and you resize it and add that back onto the system buffer, which is the input. So what we are gonna do, so that's all for the downsize pass. It's very simple, except for the part about reusing the alpha channel for something different. That I thought was a little clever move on my part. Now the next thing that we're gonna look at is the horizontal pass. Now, as you can see, it's actually a very simple function. All you're doing is you're looping through X and Y. You're scanning horizontally across the image, going from top to bottom, and you're sliding your kernel along that image. You're basically sliding this one-dimensional kernel across this image and generating the values, the blur values along the horizontal direction here. And you're doing that for every pixel. And that will blur you in the horizontal direction. No vertical blurring, only horizontal. Right? Because every individual line here is not in the processing. It's not connected to any of the other lines. It's only in the blurs, only taking into consideration other pixels on the same horizontal line in this step of the blurring. That's what you do. Now, the important thing is the values used in this array here, which is our kernel, and those are calculated. Well, the formula is right here. Let me show you. Ooh, that's ugly. Let's get rid of some other bullshit. Yeah, so this is the general formula for the Gaussian. This is the normalized formula. So what this is if you sum up all the values under the curve, then the result should be 1. That's what this scaling does. It scales this down so that when you sum underneath the curve here, the result is equal to 1. So it's basically saying that the integral from infinity to negative infinity of this times dx is equal to 1. That's what this term ensures here. Now, the reason why we would want to normalize generally is that when you multiply by something like the Gaussian, or when you do the convolution by the Gaussian, if it's greater than 1, you're going to amplify your signal. You're not just going to blur it, you're going to blur and amplify. And if it's less than 1, you're going to attenuate it. So normalization means that you're only blurring, you're not changing the actual the intensity of the signal. As we'll see later, this doesn't actually mean anything, but I added it into my formula just the same. It doesn't hurt. You'll see what I mean in a second. Let's take a look at where that's generated. Well, first off, in Chili Math here, we have the Gaussian, and this is just that formula I showed you there. Nothing amazing in here. Some square roots, some exponentials, just some math bullshit. I made it a template so you can use floats or doubles or whatever you have, but it's not going to work very well for integral types. I'll tell you that right now. And then we use this Gaussian function in the Bloom processor in here. So here we initialize the kernel float. The diameter of this is set down here, and I've got a diameter of 16 pixels. And then we loop through. X goes through the diameter, and we generate the Gaussian here, which is absolute value, float, x minus the kernel center. Now the thing about this, I'm not sure why I need the absolute value here. It shouldn't make a difference, but x here means, what does it mean? It means the x position in here. So when x is 0, that should be the center of our kernel. But in my loop, x is 0 over here, and then x is 16 over here. So what we got to do is we've got to subtract the center of the kernel from x. Yeah, so that means that x is going to start at -8 and go to +8 instead of starting at 0 and going to 16. So that's what we do here. I'm not sure why I have the absolute value here. It might not be necessary, but whatever. Now that's the first parameter to the Gaussian. I didn't actually talk about the parameters. That's a problem. There's two parameters. X is obviously just the coordinate here that you loop through to get the output. But this parameter here, rho, this determines the, I believe it's the deviation, or yeah, something like that. I forget the name right now. But what it is it's basically the fatness of our bell curve. So if you have a large rho, then I believe you're going to have a curve that looks like this. And if you have a small one, you're going to have a curve that looks like this, a very specific curve, or a very general one. That's going to determine the roll-off of your normal function. You want your normal function in general to roll off so that it's very close to 0 when you reach the edge of your kernel window. So I've basically determined that diameter divided by 6 gives us a very nice value. And that's what I'm going with. But anyways, I believe I saw that on a website somewhere. It doesn't matter. So we generate the kernels, the floating point values for the kernels. Then we have to get the integer values. And we get those by basically scaling every kernel by the value of the center value. So the center is going to be the largest value. So we scale it so that the center value is scaled to 1, and then they all go smaller from that. So you see, because we're doing the scaling here, we didn't need the normalization here at all, because we're scaling the whole thing anyways at the end. So this was actually useless, but you know, I added it in if you might want it for other applications. In this case, though, it wasn't needed. So we scale all of the coefficients here in the floating kernel so that they're normalized to 1, and then we multiply by 255. So now we get values from 255 to 0 for our kernels. Now the next thing I do is I sum up all of those integer values, and that will give us the total of all the kernel values that we can use later to divide, right? Because we're doing convolution, we're multiplying by all those kernel values, and then we're summing all those multiplications together, and then in the end, we can divide by the sum kernel so that we get a normalized value, right? And here I divide the sum kernel by something called the overdrive factor, because in Bloom we don't just want to blur, we want to blur and actually amplify, and the overdrive factor will allow us to control how much amplification we want. A smaller kernel means less dividing in the normalization, means more amplification. So, and then we just clear the V buffer and the H buffer, because it starts off with garbage. And that is how we initialize our kernels. Now that we have our kernels initialized, we can go into our passes. Now, like I've shown you, this one works exactly the way I showed you. The horizontal one works basically the same way, not the horizontal, the vertical one works the same way, only now we are scanning in the vertical direction and moving from left to right. That is one change. Now the other change comes from the whole situation of fringes and all that bullshit. So when we do our horizontal scan, let me just get on here. When we do our horizontal scan, we have a horizontal kernel, and we scan this way, and our output is going to look something like this. This is going to be where the output is. But this region here, at the right and left fringes, there's going to be no output, right? Because obviously the kernel can't go past this region here to produce this output, because there's no data here. So the left and the right fringes have no data, and the rest has, properly horizontal blurred results. Now we're going to apply to this situation here, we're going to apply vertical. And so when we do that vertical, this is all garbage. We don't want to process this. It doesn't mean anything. We only want to process the stuff in the middle. And that will give us a result like this, where this region here contains good data. This wasn't transferred over because it wasn't, this was the fringe region. And this wasn't even looked at because it contained garbage from the beginning. And the way we do that is we basically just set our starting x equal to the fringe size, and our end condition is the width minus the fringe. So we're not going to take a look, we're not even going to look at that. And then we start to 0 again. We run to height minus diameter. This one, same deal, we want the width minus diameter. And we just multiply all the corresponding values in the buffer by the kernel. We add those all together, and then we divide by some kernel, which is our normalizing factor. And there you go. You've got your horizontal pass, you've got your vertical pass, everything is fine. Now here's where it gets a little complicated. Now we have to do our final pass. There's two things you have to do. You've got to resize the image back to its original size, and then you've got to add that result onto the stuff that's already on the back buffer, and that'll give you your blur. You want to add it, and you want to saturate. So if you're adding two very large numbers, you don't want them to roll over to 0. You don't want a very bright original image plus a bright blur equals a very dark region. So you have to, you got to make sure you clamp those values to 255 when you're adding. So now the difficult part of this is the upsizing. The adding is simple. The upsizing is complicated. You have to do something called bilinear filtering. So I'm just going to talk about bilinear filtering for a second here. If I can find it on my... Here it is. So let's say that these... Not on my layer. Let's say that these red dots, or these blue squares, whatever you want to say, these are the small size pixels, the downsized pixels. The red crosses are the centers of those pixels. Now, for every one of these pixels, we want to generate 16 upsized pixels. So we've got to sample inside these pixels 16 times. And the way you sample is basically as I've shown you here. This is how you organize the sample points inside of the downsized pixels. Now, the way you generate the values of them, the way you sample, is you take their relative positions within these downsized pixels. So you look at how close it is relative to the pixels that surround it. So this one's surrounded, this pixel here is surrounded by these 4 pixels. So the first thing you do, you want to blend these 4 pixels at some ratio that will create a smooth gradient along your image. The way you do it is, first off, you basically do linear interpolation twice, and that's why it's called bilinear. You do linear interpolation in the X direction and then in the Y direction. I believe in the code I actually do it in the Y direction and then the X, but it doesn't matter. What matters is basically you take the top pixels and you blend them in their X direction depending on, you know, where the pixel that you want to sample is at. So this pixel is here. So we're going to blend, let's say these 4 pixels are A, B, C, D. So what we want to do is we want to blend basically 1/4, we want to blend 3/4 A plus 1/4 B, and we want to go 3/4 C plus 1/4 D. And this will give us AB primed and CD primed. So this is AB primed, this is CD primed. Then we take these 2 intermediate results and we blend them in the Y direction. So we go basically 3/4 AB primed plus 1/4 CD primed equals pixel. And that's how you do it. And you do that for every single pixel in here. Now there is a small problem, and that problem leads to bullshit. It leads to my code being very long, but doesn't make my dick any longer, so I don't know what the use of it is. Now, what you got here is this works fine for all these pixels here, these pixels here, these pixels here, what about these pixels here? Fuck, that doesn't even look good. What about these pixels right here? What are they going to blend between? They've only got 1 pixel. Yeah, they don't have anyone to blend with. What's over here? What's over here? We don't know. This is outside of our image. So what the solution I have is I just clamp these 4 pixels. It's very small. It doesn't even look that noticeable. Just clamp these 4 pixels to this value here. So set these 4 pixels to this value because you've only got 1 pixel to work with in this situation. And that's that. So corner pixels, set them to their corresponding downsize pixel color. Don't blend at all. These pixels here, what we're going to do is we're going to blend between this one here and this one here, and then we're going to set them all to the same value. So if this pixel was M and this pixel was N, these 2 pixels here would be 3/4 M plus 1/4 N, and so forth. This would be 3/4 plus 1/4. All right, so it's a little complicated, but basically, this distance here is 1/8, and the distance between these is 1/4. So what you want to do is, for example, let's say you're gonna find the value of these pixels here. You're gonna do 1/8 M plus 7/8. Fuck, I did that backwards. 7/8 M plus 1/8 N. This is this calculation. But for these pixels here, you're going to do 5/8 M plus 3/8 N. And then for these pixels here, you're going to do 3/8 plus 5/8. And then here, you're going to do 1/8 plus 7/8. So it's a little complicated because the starting points start at 1/8, but the steps are 1/4. That's how that works. So rewind and all that stuff I said about 1/4, just replace that with like 1/8 plus 1/4. It's mildly complicated, but if you look at the diagram, you'll see that the distance between this and this is different than the distance between here. It's exactly double it. And that's why you get that 1/8 and 1/4 bullshit. You'll see in code. Of course, in code, we're not working with 1/8 and 1/4. We're working with like 32 and 64, 96, bullshit like that. But it's the same idea applies. So let's look at the code, shall we? So code is dealing with all of the corner cases and the edge cases. And that's why it's so goddamn long. Now these size t's, they refer to either indexes into the input buffer or the output buffer, or they represent X or Y values. They actually have both, and it's complicated. It's not the best situation I know. So for example, this size t in fringe means the size of the fringe of the input. I don't know. Ignore that. It's not that important. What is important is the code here. So I've created this little, whatchamacallit, lambda function here, and all it does is it takes an input value, 3 input channel values, and it adds them to some output value pointed to by a pointer, but it makes sure that the result does not exceed 255, because, you know, the channels are 1 byte values. If you exceed 255, just roll over to 0. That would make a very strange looking image. So that's all this does, is it just adds and saturates. Now what we're doing here is we're getting the R, G, and B from the input value, the very top left pixel of the input. And that is ignoring the fringe. So in top left is just, the input width plus 1 times the fringe. And that will give you, let's see here, where's our dumb kernel convolution 2D thing here? I've got too many goddamn layers here. It's hard to freaking figure out where everything is. Okay, so that'll give you, I'm just going to draw it because that's faster. So this is our downsized image right now, all filtered. And the fringe area is, 8 pixels. It contains garbage. That'll give you this, right? So this is our in top left. And we get the RGB for that. And then we saturate that to the out buffer, right? Because we're not blending between anything. For the top left corner, all we're doing is taking those values as is, these values here, as is, taking this value as is and putting it for these 4 pixels. That's the top left corner. Now the center, we do the same thing, but we have to do the blending between, like this. Fuck you. Where is my layer? Here it is. So we've got a blend between this pixel and this pixel now. So we got to do 4 blends to get these 4 pairs of values, and we're stepping by 4 output pixels every step in the whatchamacallit, the loop. So here, our loop here, this X value represents the X in the output, and yes, this represents the 2 pixels in the input. The base X is the calculation, how we calculate the input index from the output index of X. And then we get the channels for the two values, and then we basically blend them together. So we start with 32, which is 1/8, and then 96 is 3/8, and we go just like I said in Photoshop. And we just do the add saturate for 2 pixels, same value twice. P out upper, P out lower. So these pointers point to the upper row and the lower row for the center region. Then we do the 4 pixels in the top right. And now we're able to do the center rows. Now the first 2 pixels in the center row are going to be the same deal, right? Look at it. These first 2 pixels of any given row are going to be this bullshit here. We're blending between 2 pixels. So we do like we did up there, but only in the vertical. It's the same idea. First 2 pixels, add saturate. And we're doing this, you know, for 4 rows at a time, because we're stepping in the Y direction now, we're stepping by 4 at a time. Then we do the center pixels, which is all that bullshit I showed you up there, blending between 4 pixels. First we blend, in this case we're blending in, what is this? We're blending in the vertical direction first, I believe, right? Because we're blending pixel 0 and pixel 2. So looking at our diagram, this would be pixel 0, 1, 2, 3. And we are blending pixel 0 and pixel 2, so we're blending in the vertical first, and then we blend in the horizontal, and we output. And then we blend in the vertical again with different values, and then we blend in the horizontal and output. And we're doing that. We've got 16 altogether. Then we do the last 2 pixels, which is just, again, the blending between 2 pixels. And then we do the bottom, which is, again, the 4 pixels in the corner, in the center, blending between 2, and then the 4 pixels in the corner. And then we are motherfucking done all this bullshit. So, you know, there might be a better way of writing this, but this is the way I went with. I pre-calculated a bunch of this stuff just to make it a little faster. But it does make it a little less easy to read. Instead of using X and Y everywhere, I'm just using one-dimensional indexes into the array, which can make it a little more difficult to read, but it cuts down on the amount of multiplication that the CPU has to do to calculate indexes. And that's that. That is the upsize blend. All right, so here is the result, the end result, obviously. Let's press enter. All right, so here we got the game. Let's just move around a little bit. I want to show you, because I have the, right now I have the thing set up in Go to output all of the intermediate results of every frame. So, should be able to go to game. No, that's not what I want to do. I want to go here. So here you can see all of the intermediate results. Frame A initial. So this is, what's the size? 1088 by 832. So this is the whole thing with the fringe and everything, not downsized or anything. Frame 8 initial 200, 300, 400, 500. So this is the 100th frame, 200th frame, so forth, so on and so forth. Here, right? So that's that. This is it after it's been downsized by 4 in every dimension. So there's the downsized version. It's the same thing, only it's been downsized. It makes sense. is it? Down. Now here's it after being horizontally blurred. So this is only being blurred in the horizontal direction. It's hard to tell at this point, but that is actually what has happened here. You can tell, like if you look at this thing here, you see that this is a very sharp end here, whereas you get a blurred gradient in the horizontal. In the vertical, you get places here where it just ends really sharply. Then we go to vertical blur. And now you can see you've got the blur in both directions. And you can see here that this left and the right side are just garbage for the output here, because it doesn't actually look at those at all. And then what else? Actually, top and bottom are also garbage in the vertical blur, right? In the horizontal blur, horizontal, left and right, there's nothing in here. It's just empty. And in the vertical, you've got the unblurred versions here. The whole fringe is not being processed because it can't be processed. And that's the whole point of the fringe. And then here is the final version after it has been upsized and added back to the original. Looks like this. And the fringe, as you can see, that's just the original version as it was. It's not touched, and it doesn't get copied to the back buffer. And that's how it goes. That's how you do. That is how we do. And if we take a look at the performance, let's just go quickly to, where is it? Bloom processor. And we're going to get rid of all this stuff here. And I believe in game, yeah, we have a timer for the frame timer. So we're going to do this. Now mind you, this is the values when I'm recording, but it's not that much different from the values when I'm not recording, I believe. So we'll run the thing for a little bit. The red looks pretty awesome too, actually. And then we'll press stop, and we'll go to our good old friend, open file folder, bloom.txt. For some reason, this is not opening the way I want to, so we'll go edit. And here we go. So we've got on average, about 12.5 milliseconds to process the bloom for the screen. And that's pretty tight. I mean, I'm still getting 60 frames a second, but there's not much room left for other processing. Because, I mean, we need to run 16 milliseconds in order to maintain a 60 frame per second rate, right? So 12 milliseconds, that's most of our time just spent doing our post-processing. It's not very good. It's an expensive operation. It works on the entire screen, even after applying all of our optimizations, splitting the filter up into horizontal and vertical and downsizing. We're still running at 12 milliseconds. So the answer to how we make this much faster is SSE. SSE can speed this up by a fuck ton, like by over a factor of 4, close to 8 times faster, I believe. And on top of that, we can also do multi-threading, but that's a little bit later. In the next episode, I'm going to show you how I optimize this using SSE to make it a hell of a lot faster, and such that it does not impact the performance of the game in any significant manner, without sacrificing any of the quality of the filter. But that is, as they say, another story, and for today, I think I'm done. So I hope you enjoyed the video. If you did, click the like button. It helps a lot. And if you have any questions, you can ask, you can leave a comment, or you can talk to me on the forums. The link is below in the description. And I will see you later.